All right, welcome back, everybody. Today we are finishing up the last major conceptual part of the first lecture series, which will be on continuity and the continuity equation and what continuity even means. So after this, we'll be looking ahead to do some examples. Yeah, okay, so let's hop right in. So continuity, what is it? It's written I1 equals I2 or A1 V1 equals A2 V2. What does that mean? What are these things? What are we talking about here? So let me draw a little picture. So when we talk about continuity, what we're really doing is we are making a statement about conservation of stuff. So if we have some fluid system, say, I don't know, let's just do something easy. Let's do a pipe that narrows. If we have some fluid system, we have some pipe that narrows. Here we go. Throughout this tube, there are certain cross-sectional areas. Call this A1. Call this A2. And through those cross-sectional areas, some fluid is flowing. So I'll say that current is flowing to the right here. I flows right. So some fluid is flowing in this direction to the right. Cool. So at each point in the pipe, we can associate that point with some speed v of fluid flow. So v here is, little v is for velocity, not volume. And I'll try to do a good job of putting a little squiggle to indicate lowercase v for velocity. So this is velocity at point 1. Here's velocity at point 2. Okay, so what the conservation equation says is that the stuff entering one region of the pipe for a connected pipe, a simply connected pipe like this, must be the same as the stuff exiting that section of pipe, even if the cross-sectional area is a little different. So yeah, so written out, we can write this in a couple of ways. We can write it just as I1 equals I2. The current at the first cross-sectional area is the same as the current out of the second cross-sectional area. Or we can describe it using this form. A1 times V1 equals A2 times V2. Now it's not immediately obvious why these are the same. So let me try to show real quick why that is. So say that this little cylinder here, I would just tracked its movement through time. And let's say I watched it for 1 second. So I'll say after a delta t of 1 second, how far has this thing moved? It's going to have moved forward some amount. I'll mark it in blue. So it'll have moved forward some amount, right? Okay. Similarly, over here, if I let time move forward a little bit, so I let this little cylinder, or this little circle, if I keep track of the water passing through this circle at one point and let 1 second pass by, I can watch that little patch of water that was here move some distance forward. Okay, to this new area here. Okay, so the claim is basically that the volume of this little shape, the amount of water that moves forward in 1 second in this first area, is the same as the volume of this second shape, the volume of water that moves through this other area in 1 second. So hopefully that makes sense. It's conservation of volume in the sense that whatever volume of water moved through this area in 1 second must be the same amount of volume of water that moved through this area in 1 second. Notice that the amount of distance it covered on the right side is longer. So it had to move faster in order to push that same volume through a smaller cross-sectional area. So V2 is like greater than V1 if A2 is less than A1. And again, the reason for this is because it's like a volume conservation. We need the same volume of water to flow through two different cross-sectional area sizes. Okay, hopefully that helps. So again, it's a statement of volume conservation. Volume conservation. All right, this tends to be a little bit of an intuition breaker for people, so I have two analogies that I like to use. The first one is of traffic. So imagine for a minute that you're just driving down the road. Okay, you're driving down the road. It's a 2-lane road, let's say, whatever, or you're biking down the road if you're a biker, whatever it is. You're biking along or driving along. We'll stick with the car for the sake of ease. So you're driving along and then you hit a traffic jam. Okay? Let's say that there's like 50 cars in this traffic jam. Lots of cars, jam. Okay. And you've been driving this route every day for the past 12 years. You know it's cool. It's going to take you about 20 minutes to get through it. Whatever. No big deal. But the same number of cars always seem to be in this jam. It's always 50 cars. They're just hanging out, same number of cars. The traffic jam never really grows or gets smaller. It's just in dynamic equilibrium. So there's the same number of cars jammed up here, and they move more slowly in this region. So because it's a jam, we've got a slow moving section of cars. Okay, you notice that in the fast moving section back here, let's say 3 cars per second come to the backside of the traffic jam. 3 cars per second, which is kind of a lot of cars actually now that I come to think of it, but we'll deal with it. So 3 cars per second come to the back of this traffic jam. However, you notice that again, 50 cars are stacked up in the middle here. This corresponds to like the volume of water in a given section of pipe not increasing or decreasing. It would have to like break the pipe walls, right, in order for the volume of water to increase or decrease. So in order for the number of cars to stay the same, while other cars are being added to it at a constant rate, that means that on this end, the far end of the traffic jam, you've got to have the same number of cars leaving per unit time, 3 cars per second. So that's basically one analogy I like to use for the conservation equation. The stuff entering the jam, the stuff entering the junction of the fluid circuit, the cars entering have to be the same as the cars exiting. Otherwise, you'd have a jam that grows. In other words, a non-equilibrium situation. In the context of fluids, that would mean like increasing the amount of volume that's that the fluid is taking up in that region, which isn't possible. You'd have to break your pipe. Okay. Another example that I like to use is one that folks who grew up in the suburbs might know, or just in general, I don't know, is the thumb of the garden hose. So if you have a garden hose, you've got some region where, here we go, you've got some region where you've got water flowing through this cross-sectional area, A1. If you put your thumb over part of it, nice fingernails, very well kept. All right, if you put your thumb over part of it, you're effectively making the surface area smaller. Wait, let's change my notation. We'll put A1 here, A2 here. There we go, that makes more sense. This little crescent shape, that's my new cross-sectional area. So whenever you put your thumb over the garden hose, one thing you might notice is that the water comes out faster. It spews out at a faster rate. Or not at a faster rate, I shouldn't say. Like not a faster current, just a faster velocity. So doing some quick like visual math here, if the current has to be conserved, I1 has to equal I2, then that means A1 times V1 equals A2 times V2. Or in other words, because my A2 is smaller than my A1, my V2 has to be larger than my V1 in order for these two things on opposite sides to be the same size. So when I reduce my surface area, my speed becomes faster. When I increase my surface area, my speed becomes slower. Cool. I think that about wraps it up for continuity. We will bring it on back next time with some intuition builders and a wrap up. Thanks, y'all.